Hello everyone. Today we have the pleasure to have Shikai Fang with us, who will talk about his work on dynamic tensor decomposition.
Hey, brother, I can't hear you. It sounds like you're reading now.
Yes, I'm reading just I'm this. So Shikai is a final year PhD candidate in computer science at the University of Utah. His research focused on Bayesian machine learning, tensor learning time series, and AI for science, with the vision to push AI's frontiers to challenging higher order data scenarios with tensor-based representation learning. He also has experience in research labs of industries such as Morgan Stanley and Alibaba Damo. Thank you so much, Shikai, for accepting our invitation, and the floor is yours.
Yeah, thank you. Thanks for introduction. Uh, and let's begin today's talk. Today's title, I may introduce our work that denote the dynamic tensor composition for the neural diffusion reaction process. Actually, it's the spotlight paper published on the Neural Apes 2023. And actually, the work is worked together by the Zheng Wang, Shikai, myself, Shibo Li, and Xiayan Zhe. And today I will, on behalf of all the authors, to present. And actually, I'm from the University of Utah, from the Ski Institute. And let's get started. So we start from some background about what is tensor and what is the tensor decomposition. So what is a tensor? A one sentence short introduction is tensor is just a multidimensional array to represent the high order structured data. Actually, this kind of data structure is everywhere in the data science scenario. For example, in the climate system, if you want to identify like the temperature in some locations, then the temperature, you can treat it as the interaction about specific region, specific the topology, and specific the weather. And another most well-known scenario for the tensor is the online advertising. Is the basic the recognition system. So whether a user will buy a movie or so buy items, the interaction, whether this user will buy, can be treated as an interaction about specific user, specific weather, a specific movie on the specific site and device. And a similar example, I mean, like I show here, is the traffic flow. If you want to travel the speed of some road in some cities, I mean, the interaction, the speed of the traffic flow can be seen as the interaction about the city, about road, about the population period. So for tensor data, actually, for each entry, actually, it's just an index, different index actually represent different objects. And the value actually is the interaction about the multiple object indicated by the index. So here is the tensor data. And how we handle or analyze this tensor data. The basic rule is just the tensor decompositions. But here, I mean, the general idea for the tensor decomposition is just to learn a low rank factors of the high order tensors. Here, I just show you our most classical and most simple example about tensor decomposition on the 2D. So it's become a matrix decomposition. And the name for this is called collaborative filtering. So, this problem is very classical. Actually, it's raised, I think, from a computation by Netflix, I think maybe 15 years ago. Actually, because in the Netflix, in their business, they want to recommend the movie to the users. And how they formulate this problem is they're saying, giving a rating matrix and the row of the rating matrix may be different users. And the column of the matrix is different, like the item or movies. And the red items here is the observed the score given from some users to some movies. And our goal is we want to incomplete and we want to complete the full rating matrix. And if we can do that very well, actually we can base on this rating matrix to the recommendation. And actually this tool is the collaborative filtering. I think it's the initial version about the recommendation system we use today. And the ideal the low rank factorization we try to learn two parts about the factors, one factor for each users and one factor about each movies. You can treat it as their maybe the column about its user factors is a two-dimensional vector, and that is embedded about some specific user and their movies. So use this very simple idea, actually, I think this solution become the champion solution for the challenge faced by Netflix. And actually, after that, after 50 years ago, the tensor decomposition become more and more popular, especially with the boosting trend about their recommender system, their social media or something. And here is only we talk about the 2D case, how we learn the low rank for the high order tensor. If we extend it to a high order, I mean 3D, 4D, and we got the general tensor decomposition. For here, I list you three, the very classical and most well-known tensor decomposition, the CP, Tucker, and tensor trend. If you're not very familiar with the tensor decomposition, you don't have to go to very deep into how these formulas is exactly mean. I just want to get a high level idea here. So no matter what are the traditional tensor decomposition or CP Tucker tensor trend they look like, the key idea is we want to try to learn a set of the low rank factors as the representations as the embedding of the real world object. And we use different linear algebra, or right now it's a nonlinear method, to combine its factor together and finally to reconstruct the high order tensors. So here is I can see the high level, the most crucial idea about tensor decomposition, just to learn set low rank factors to represent the high order tensor. So if we get this very clear, and we talk about the data, we focus on today's work. Actually, is the temporal tensor data, because the general tensor data, just I'm saying, it's a very long history, very classical topic, and many methods have been proposed. The most like the Tucker decomposition is proposed, I think, in the 1960s. It's almost 60 years ago. So right now, as a tensor people, as a group, we focus on tensor. So one of the new challenge we should focus. I think one direction is we focus on the temporal tensor data. I think another good name for this is the tensor value time series. But here, I also give you two examples. The first example is still a region, a tensor-based spatial temporal the weather data. At each time step, you can observe a tensor, a 3D tensor, maybe the temperature about a region. So each temperature here is the interaction about region, about your observation site, and different weather factors. And this tensor actually is changing through the time. And another example on the right side is about the social network. You can see the social network as the 3D, as the 4D tensor, as how the user send the message to another user in the different location, use different message type. And of course, the network topology, the connection about this tensor is changing over the time. So compared to the classical tensor data, we only focus one tensor. But here, at each time step, we observed a new tensor and how the tensor structure are evolving through the time. So you can also call it a tensor value time series, because at each time step, you observe a tensor. Actually, and this I think is the setting and the scenario is everywhere in the real world scenario. But actually, I think it didn't get enough attention from the whole machine learning group. I will show an example. How the current, the people do the time series, do the dynamic, can't use the current method to capture this. The example I use here is the wind power prediction. It's a very classical scenario, and actually I used during my intern in the Alibaba demo. They have lots of the industrial scenario like this. The goal of this task is do the prediction on the wind power in the different turbine. You can the turbine here on the sea. If you, the goal is given the historical sequence and data about the power prediction. And we want to do the prediction, we want to do the imputation, which is the classical task for the time series. However, if we only use the classical time series, the choice, they become a classical the multivariate time series problem. You feed this historical sequence in some LSTM, in some transformer, and then you do the long-term forecasting, you do the imputation. That's good. Actually, but however, this setting actually cannot perfectly match what we face in the real problem. Why? Because we know when a turbine is working, when it's just generating the electricity, it's not only about the historical sequence. It's about what the current climate is sunny, it's raining, it's windy, and what's the life, the set of the turbine is a big one, is a small one, and because in the sea, what's the ocean current? It's very mild one, it's a serious one. So outer variables actually works together and finally reflect as the time series problems. And actually, if we will combine this order variable together, we got a temporal tensor. We want to predict the power about each station. Actually, you can see the 3D tensor. The wind power at each time step can be the interaction about different climate, different turbine, different current, and they're crossing with a time, and we get a power. And currently, I think that the classical time series community didn't have a good toys to handle this. And here, I think the temporal tensor is a good toy to handle this. And as we talk about the importance about the temporal tensor and how can help with the real world the hard challenge and how to handle this temporal tensor. It's quite a new challenge. For the whole tensor community. I think maybe you check the tensor paper published maybe 5 years or 10 years ago. You'll find if some tensor data set is with the time step, the trivial solution is we just drop the time step, or we just do the average over the time step and finally get one tensor. And of course, this process is too raw, and we are losing very important the temporal information in the tensor. And another more advanced solution, even the classical solution to handle the temporal tensor is we argument the tensor itself with the discretized the time mode. For example, we initially have the 3D tensor shown here, and each time step actually is the time variant variables. And we just expand this tensor from 3D to 4D, and the fourth dimension is just a time step. Actually, we can do this, but actually, this solution still have some problem. First is the sparsity. As we know, if we have the experience to plan with the tensor data, you will find most of the tensor data in the real world is very, very sparse. And right now, you expand the sparse tensor at the actual dimension for this, the sparse problem become more hard to model. So you make this problem more harder. And another more crucial problem, just to expand the tensor is you ignore the temporal continuity. So what does that mean? In the classical tensor, we know the index of each mode, like the T1, T2, or the I1, I2, they're just the index to indicate different objects. There are no guarantee. Like the T1 and the T2, they actually be closer because every object, every index, just indicate the independent object. But however, these dimensions of the time, they are the continuities. The entries with T1 and T2, where T1 and T2 should be very close, the entries should be somehow be more closer. So that's the continuity constraint about these temporal things. However, if we travel the temporal tensor like this way, we totally ignore and lose the temporal continuity constraint, and whereby the model cannot actually the temporal things can model it very, very perfectly. And all the tensor community, find this problem. So in the recent years, very, very recent years, maybe just past 3 years or 5 years, there's some work, we're trying to find a new framework to handle the temporal tensor models. And here I list three papers published on the top tier the journal or conference. And what the linear formulation they put to handle this is model tensor as this way. Is we add each tensor entries with time variant as a time variant approximate with a time variant weight WT here combined with some the statistic factors. The static factors actually this way is, just match the classical tensor decomposition. Like there could be the CP, could be Tucker, could be the tensor trend. And besides that, we add a weight and let the weight evolving with the time. And of course, this formulation is very clever because it makes the problem become easy. It decomposes the static parts and the time evolving parts. And it's quite easy to inference. But actually, this formulation, as I claim, is oversimplified for the real problem. Why? Because actually, in the real world, the involving factors, represent the embedding of your real world object. They are dominant in many cases. Just recall the example I gave about the wind power prediction. If your wind the wind power prediction, there is changing through the time. What is actually involving? What is actually changing? Is your climate is changing, your current ocean current changing, the situation about the turbine is changing. You cannot say, yeah, I just use a changing weight to capture all these weight changing, or capture all the time variant changing in these factors. That is oversimplified. And of course, you cannot get a very good results through these oversimplified formulations. Yeah, good questions. For here, for example, if we will use the CP decomposition here and the WT, we could go back to the formulation here. Yeah, you see, we will use the Tucker decomposition. Tucker decomposition, if we transfer the classical Tucker decomposition to a time variant, to a temporal tensor setting, we just assume this Tucker core, this W here, he is a time varying functions, and use this to free the time varying entries in the tensor. And if we use the CP decomposition, to handle the temporal tensor and transfer the classical CP to the time varying version, we make this one here actually as the time varying weight, and the factors is still the static. So it's just like how to transfer the classical decomposition to make them fit the temporal tensor. And the general formulation is no matter what the decomposition you choose, you keep the factors, you keep the low rank factors as static, and you add the actual changing weight, maybe Tucker core, maybe the weight about the CP, or even add the actual weight here about the tensor trend, and to make them changing with the time. And then your classical tensor decomposition become a time varying temporal decompositions. So it's all clear. Actually, I think so. Actually, here the formula here is not it's not exactly match. The each formula presented in each paper, because like the three paper presented here, some of them use the CP, some of them use the Tucker. I'm not sure if you use the tensor neural network. I'm not sure whether you can specifically use this, but actually the general ideal, I think is universal for all the tensor decomposition. If you use the tensor neural network, of course you can actually add an extra time varying weights or something combined with the current decomposition and make it with this way. And actually, this formulation is very easy to inference, and actually that's the advantage about this one. Yeah, thank you for your questions. Yeah. Like I'm saying, the current formulation is easy to inference. It's very easy, but actually it's oversimplified. And our goal. So our goal here, the motivation of our work is, as we think only learning some time varying weight is too simple. And how about we just learning the dynamic vector trajectory? We just assume we just for each representation about the factors, I mean representation of the real world object, we assume there's a time varying function. We can do this. We can not only get a more powerful model because the capacity of this model is more powerful, and another we can actually we can get some gain of the interpretabilities because we know each embedding of the real world object how they changing with the time. If we can do this, I mean, actually give a more powerful model and more the explainabilities models. And the hard thing is how to exactly do this, how to learn the dynamic factor, the trajectories through the time. So actually, we have two challenges here. The first challenge is how to model the latent dynamic, the factor trajectory with the efficient and flexible ways. And the second challenge here is, I think, is more hard, is in the classical dynamic condition, so each factors actually we assume they're independent. However, in the real world, there are different factors. Of course, they are correlated. Then how to model the possible dependency or the possible correlations between these co-involving factors. We record it's a very hard problem. It's not only the dependency about the factors. Also, each factor itself is a time-varying functions. It's evolving through the time. Then how to do this together? That's the challenge of the most challenging part about this ideal. And our solution for this is our insight to handle this challenge is we want to build a graph. Actually, we want to build a graph to handle the dependency about involving factors. So how we gather the builder graph is ideal here. So actually, it's a little tricky, but very interesting. I will show you. We know because I used to have some knowledge about the graph learning, like graph neural network, and I found because given your graph, you can write down a matrix to represent this graph. Maybe I'm like the adjacent matrix or the Laplacian matrix. So there's the one-to-one mapping between the graph and the matrix. And as we know, the tensor is the general case about the graph. So if we give you a tensor data, can we still find some like graph-like construction or graph-like the structure to represent the connection about this tensor? If we can do this, given a tensor and we build a graph, and then we can build the dynamic factor or dynamic tensor like a dynamic graph problems. So is that all clear here? I will give you a detailed explanation in the later in the next slide. But here I'll just give the high level things. How we just think of these problems is we want to build the bridge between a tensor and a graph, even maybe some special graph, like the hypergraph or K-hypergraph graph, and to encoding the inherent nature about the tensor. And then record we're handling the dynamic tensor problems. But if we can handle the tensor to graph, then we finally to build a dynamic order on the graph. Actually, it's the graph constraint ODE or the dynamic process on the graph. So there's the high level motivation comes from. And here is just a very highlight the highlight solution about our work. So actually, we first build a graph. This graph is just built from observed tensor data. Actually, for example, we're showing the green table, the one row here. Actually, with their interaction with their entry is interaction about I, J, K in different mode and time step, and we get a value. And then based on these observations, we just build our edge actually in the graph, the three green edge here. And actually, that's the one graph edge, one set of graph edge. And then because we want to model dynamic process, then we assume on this graph we built, there are two kinds of the dynamic process. The one is called diffusion process, and the second one is called reaction process. I will give you the detailed introduction in the next slide, but here just give you a high-level idea. With such motivation and insights we introduced, the final key idea to do this is we want to transfer the dynamic tensor or temporal tensor problem to a dynamic process problems on a separate on a K cover the K part graph. So for detailed introductions, first, how to build a graph from a tensor data. The first, I mean, here is the detail, the procedure. The first, for each graph node we want to build, actually, it represents one the tensor factors in the initial tensors. So how many tensor we have, tensor factors we have, so how many nodes in this graph we have. And then second graph, how to define the graph edge. I mean, how to define there is a connection between some node in this tensor. We're defined by the tensor entries. Because we know in most of the tensor are very sparse in the real world. So we observed one entry in these initial tensor observations. We just build a graph edge between such nodes. So just like an example on the figure I just talking about, we go through it again. I mean, for these green tables, we just observed one tensor entries. And then what I'm doing is we just add three green edge in the graph to build these three nodes together. And there is one set of the edge in this k-separate graph. And the edge weight, the weight on this graph actually is the learnable parameters. We don't assign the weight based on the value about this node. So we observe entry, no matter what the value about this entry, we build a connection in the graph. And this first step, just a first step, how to build a graph from the tensor data. And the second problem is how to model dynamic process, how to model the dynamics things on this graph. Actually, here we use the idea about the diffusion process on the graph. So what does that mean? So what is the diffusion? Right now, maybe when people talk about diffusion, there sounds like they're denoising to the generated image. But actually, the general definition about the diffusion, like I showed here in the in this table, actually, it's just a concentration change about some density, about some heat, about some concentration from the low density, high density area to the low density area. So that's the general definition about diffusion process. And right now, just thinking, we just define the diffusion process on a graph, like I'm showing here. So one node is connected to several nodes. And we will give some initial value about at each node. They have some concentration on each node. And how this concentration, it can be changed through the edge with the other edge. So, and that's the ODE system I showed here. He just told you here the diffusion ratio, the changing ratio about your concentration, about your energy on each node. Actually, what is equal to the edge weights. I mean, the strength of your connection with other nodes, and combined with the concentration gap. I mean, the gap about the density or concentration of your node, your current node and your neighbor node. So there's the ODE formulation about this. And actually, I think this is a very classical formulation. I mean, called the graph ODE, or people use this to define how the heat, if you heat each node and after time involving, how the heat finally smooths over the graph. So this ODE is from the physical domain. Actually, this formula is the node-wise. If we just represent all the nodes in the graph, we'll get ODE, something like this one. And actually, the parameters about this ODE actually is all in the W. W is just the weight, the edge weight about all ODE, and A is just the sum about the connection node altogether. And actually, the W minus A, this matrix actually is the Laplacian matrix. So this actually is just a Laplacian diffusion based on the graph. So here is the diffusion. Yeah, I got a new problem here.
I have a question about
Yeah.
this
Yeah.
in problems.
Yeah.
Each node is a tensor.
Each node is a factor. You can treat it as factor is the embedding, and right here in the graph is the node embedding.
So you do a tensor decomposition and you find the factors, and then you build a graph out of these factors.
Yes, and each node here is just equal to one factors in the tensor.
I see. Thanks.
Yeah, sure. And here is the first, I mean, the process, I mean, how the changing about the factors is on the graph through the through the tensor. We just define the definition. And we think only the diffusion process is not enough. We need another process. It's called the reaction process. So like the illusion showing here. So why? Because we know the diffusion about the concentration on the graph between this node actually is more the global change through the connection. And of course, and we also find there's some local concentration trends and the self-involving about these factors. Just take an example. If each node represents each maybe their users or the users on the maybe on the island on something, and of course my attention, my interest, uh, which represents by the factor of myself. Actually, it can be influenced by my friend, by some object. If there's the diffusion process, and of course I have my own ideas. My own idea, my interest is changing by myself. It's not related to other factors. So we just based on this motivation, we build another process we call the reaction process under each node and on each factors, and actually just apply this together, and the final we got our diffusion reaction ODE on the graph. So actually, it's saying all the nodes, its changing ratio is equal to two parts. The first is the classical in the red box classical diffusion process is controlled by the connection with other nodes, and the second one is the reaction process. It's only by myself. Actually, we model it by a neural network, which takes your current embedding initial embedding and time variance sorry, at a t as the input. And finally, he will output your self-involving effect on the current time step. So here is the final diffusion reaction ODE about all the your dynamic factor is changing. It's not like a regularizer. Actually, I mean, our motivation is fine. The only use the diffusion process is not sufficient. Because if you only use the diffusion process, you have to assume uh, when the initial value about your graph is given and the edge weight is given, everything is fixed. So, but actually we find this assumption may be too stronger and maybe not fit the real application. Then we decide to add reaction process. If we think only the diffusion process on graph, I mean, given the initial, we think everything after, I mean, enough time changing. So finally, we'll find everything you get average after the embedding of your node. Each node on the graph will get an average effect because it's just the meaning of the diffusion. But of course, I think in the real world tensor, temporal tensor, with very long time step, of course, the definition, not definition, the embedding the value about your factors, they have a significant gap. They're quite different. That's not match the diffusion process because diffusion process after enough time involving everything will get there very close. So is that clear? Yeah, cool. And based right now, and we get the most crucial, I mean, formula here is the diffusion reaction ODE for how they're embedding of factors involving on the graph, and how we can just rebuild the tensor entries from these things. Actually, we just build a nonlinear neural network decompositions. So we have a very good approximation on such ODE, and we got the time varying factors here, the ULE, UR2K here, and then we use another neural network with just their MLP to combine these factors together and to reconstruct each tensor values we observed in the observed data. So with each the entry value generation formulas, we can write down the joint probability of our all models. So the joint probabilities have three parts. Actually, we have the parameter about G. G is the neural network we use to handle the nonlinear combination about the factors, and the parameters about reactions because we also model by some neural network, and the log likelihood have two parts. First two part is the Gaussian priors on the parameters about such neural network, and the third part is the Gaussian likelihood. I mean, based on current observed factors, how it matches with the object entry of the tensor. And finally, the inference about this demote, I mean, is following on this procedure. Actually, it's two-step observation. The first, as we have the ODE, the gradient tract diffusion reaction ODE right here, we can use some gradient tract ODE solvers to solve the trajectory of all the nodes on the graph. Actually, the ODE solver takes the initial value, take the time step, take some parameter like the edge weight of your graph and the parameter of your reaction process, and we get a UTM. And actually, we feed this UTM, the trajectory factors fit in the likelihood, and to maximize the joint, the log of the joint probability by the minimax statistic optimization. And this step actually is quite standard in the Bayesian-based inference or something. And the gradient of your H weight about your initial value about your each node and the parameter about your reaction process is all tracked by the ODE solver. And you can freely to first on the ODE solver and then feed in the loss function and then directly use the gradient descent methods to optimize all the things. So that's the inference about the ODE, about the mode. First, solve the ODE, call some ODE solver, and then grab into the loss function and use the mini batch stochastic optimization. So is there any problem here? Yeah, cool. Here and the last step, I will just show you some evaluation results of our work. The first is some synthetic test. We just set some use some like the exponential functions or the linear function with the different weight to assign to different trajectory factors and use this trajectory to decompose, I mean, to combine observed temporal tensor and run our models, the mode one and other temporal tensor models, and to see which one can exactly to match the ground truth of the trajectory. And even cause you can see our demote doing the perfectly to match the initial ground truth about this vector trajectory. And on the real world application, I mean, we just measure the predicted performance about our demote compared to lots of the dynamic or tensor decomposition, decomposition methods like the CPE, like the neural network based, like the ODE based or something. And of course, you see our method can outperformance by large margin because I think the reason is our formulations, because we assume every factor is the trajectory. And this formulation has the greater potential with the great capacity to handle the complex models. And more interesting things is on the right side, is we do the amplification study on the reaction diffusion process in our models. Because demote our models, we combine together with the reaction as the diffusion. And how about we only use diffusion or only use the reaction? So just match the question we just got. How about why we need to use the reaction? It's like a regularizer. From this effect, it's somehow like the regularizer. You can see if we only use the reaction, we will never consider like the graph diffusion or something. The result is quite bad. And we only use the diffusion without the reaction. We get some performance gain, but still worse than the demote. So only you combine the reaction and diffusion together. You consider global concentration changing only and along with your local concentration changing and enrobing, and you will get the best results. Then that's what we found from the ablation study. And the last slide here. Oh, we got any questions. Oh yeah. Sorry for the missing. Yeah, the R here is we choose is a rank for the tensor decompositions. Cool. And for the last slide, actually, I want to show you some because the initial goal and the motivation is we want to do the trajectory learning from the temporal tensor, and here is what we got. I mean, for both the factor and the entries, So on the left column, this part, this three stuff figure here, actually is on the real world data set, and we just plot the final trajectory learned for each vector. And you can see it's showing very clear the trend, like the first increase, then decrease, or the smoothly decrease or something. So if somehow, if you combine with this trajectory with the domain knowledge, I think you can have some more insights and explainabilities about your data set itself, and use this trajectory learning. I mean, the vector trajectory and then we can do the entry trajectory. Is showing on the right side. Actually, it's actually on two different entries. It's located 211 and 311. We just use the trajectory learning, vector trajectory learn on the left side and combine together. And you can see here's the results. The training data actually plotted in the blue top actually is quite sparse. Uh, and actually, with this very sparse training data, the trajectory about the entry actually give a quite reasonable and have some the like the how do you say that? The signal with a very clear seasonal pattern to show the trajectory. And the blue line, the GPCT, is another trivial solution to handle the continuous tensor. Actually, the alert curve about your entry trajectory is quite smooth and actually it's not fit very well with your training data. So that's the advantage and about our motivation. With this method, you can learn the trajectory, can learn trajectory clearly, both for your factors and your entries. Okay, and I think that's all the content I'm here introduced with the demote. And maybe in the last slide, I will use a few more minutes to give a broader view about my understanding about dynamic tensor, a broader understanding. But before that, I want to double check everything is clear about the demote. Yeah, we'll get questions. Okay, let me see. Let me see. Yeah. I think from the experiment result here, yes, I think increasing the rank like from 2 to 7, um, it do not I mean gather too much in the implement the prediction the performance gap. Even the worst, I think the R2 is very slightly gap. But I think for the CA traffic on this data set, I mean more rank you get the uh, I think the best performance actually is for the R equal to 3. Yeah, but actually, I think this scenario, I mean, it's always happen in the tensor decomposition, because there are some definitions they call the optimal rank for the tensor decompositions. If it's something maybe for here, the optimal rank is just a relative small, it's R equal to 3. If you use the higher rank like the R5 or R7, it's at your model more redundancy, and actually your model is more harder to converse convergence to the optimal performance. Yeah, thank you. Yeah. I know the optimal rank selection for the data set for tensor is an open question. I think it is the NP hard problems. And from our experiments, I mean, my experience on this tensor data set decompositions, I mean, somehow just start from some low rank. If you get good results, and you train a higher rank. And in the most times, the higher rank, like the R equal to 20, 100, yeah, I mean, in that case, in theoretical speaking, this will give your model more redundancy to get a better performance. However, during the training, you cannot make your model converge to other things. Yeah. No, right now, because our model is based on the neural based with the interaction together with the neural. So most of the cases that we choose here, we focus on the also the nonlinear decomposition, like based on the neural network, based on the Gaussian process. We only try the CP based, I mean, with some time varying pattern, but we don't try the Tucker or TT because we believe such baseline like the TT or Tucker, the performance should be because they are based on the multilinear. So the capacity of such model should be less than the nonlinear based, like the neuron based or Gaussian process based. So that's the reason we do not choose the simple one. We choose the harder one because our formulation is also based on the nonlinear. Yeah, cool. Yeah. Any other question about the experiments and the demote? Cool. And then we have to the some board review, some like the future work or something. And actually, I'm in the final year PhD and doing the tensor decomposition, I mean, for almost 5 years. And what I found is actually the tensor decomposition or the tensor data actually, I think it's everywhere in the machine learning, like the climate, like the social network, like the physical simulation. And actually right now, I think the different community, like the tensor community, like the graph learning community, they are used different the data type to represent this high order structured data, like the climate, like the social network. And actually, I focused on tensor, and I think there are larger community. They focus on the graph. They use the dynamic graph to the climate prediction, and also someone used the ODE group the community. They use the spatial temporal sequence. I mean, from to handle the like the climate change. And I found this kind of data type, like the sparse tensor about graph, they have their inherent connections. And the climate thing, the demote I just talked about today. I think the most important, the high motivation and insight is we found there's the connection between the tensor and the graph, or even the hypergraph. And then both on these insight and motivation, we get the most. Then, but besides the sparse and tensor, besides the tensor and graph, we still have the spatial temporal sequence. We have the complex dynamics. So is there possible to find some more general and more unified framework? We can just combine these different data type about its high order structured data together and build some very interesting work. And I think that direction is very interesting and lots of potential. If we can finally to use the tensor, maybe use the tensor to represent the ODE, use the graph to represent like the social network. I think for the graph learning, they use graph to represent everything. But actually, I think they have the potential to handle the more complex and more the challenging problem, like in the AI for science, in the even for the large language model. Then based on this insights or the believing in the connection, I think in the futures, we can find some unified framework to represent various the structured data, like the tensor hypergraph dynamic with the time series, multivariate time series. And here is the hypergraph, is the drug, the AI for drug discovery or something. And the basic idea actually, I think is the similar. It's just use the low rank surrogate to represent the high order structures. And also, I think another very interesting motivation from the demo is to apply some first principle from the science and industry to enhance the tensor learning. Because for demos, I mean, another very interesting and crucial idea is we use the diffusion process on the graph to build to model dynamic tensor. And this idea, similar idea, you use the symmetric structure, use the diffusion process, use the ODE from the physics, from the engineering to enhance the machine learning, the tensor learning. Actually, it's quite promising. That's maybe in the future we can try to encoding more and more the first principle like this one in our tensor learning and structure learning model like to make our model can better fit the dynamic and structured data. And the third, I think, is very interesting directions is about the large language model because right now people are talking about this. I think there are two very interesting directions you can combine the tensor learning with the large language model. The first is just the tensorizations. Because I think because I saw some group in our reading group working on the tensor network to compress the neural network. So I think right now one trend is can we use the more advanced tensor decomposition to decompose and tensorize the large language model, and also combine with some like the quantization technique and to make the large language model is fitting on the edge computing. And that second direction here is for here right now we have some fundamental models, and we want to apply this fundamental large language model to different tasks and new tasks, we need to do the fine tuning or they call the alignment. And one of the most popular things is do the model. It's just we just add a new branch like shown here in the figure 3. So here is a pre-trained model about large language model, and we add extra branch about this, and then do the matrix decomposition on the branch and to make the model, the large language model, to fit the new task. And here, that's the basic idea of the Laurel, and it's based on a very classical the matrix factorization. And how about we have the multi-branch here, and then the weight become from our matrix become tensor. Then can we use the tensor decompositions to do the Laurel like the ideal and to make our language model fast to alignment and fitting the multitask and the domain adaptation and for different tasks. So, but for here, actually, just on very interesting idea, but actually, I didn't go to very deep details about this idea right now. So, if you're interested in this idea, you're welcome to talk with me. Maybe we can have some collaboration in the future. Yeah. And I think that's all I have today. Thanks so much for the listening and attention. Thanks so much. And more questions are welcome. Thank you. You're welcome. Thank you.
Thank you so much for the presentation and for the
yeah, thank you.
Your general view on the topic.
Yeah.
Thanks. If there is no question, so can stop the recording maybe.
Yeah, cool. Thanks so much. I will stop share. Yeah.
Thank you. Have a good day.
Yeah,
Thanks
thank
again.
you. Yeah, see you.
Bye.